Welcome to this episode in the xtUML learning series titled xtUML Test Benching, also known as Model-Based Test. As always, I'd like to thank the xtUML.org community and all of the materials and resources that are beginning to accumulate to help people with the understanding of xtUML. And for this particular presentation, it's especially important because all of the materials for this presentation will be based on models that you can download from xtUML.org and the associated github.com repository. So please take advantage of those. The agenda is very short and simple. This presentation today will focus largely on the how-to, the hands-on of building an xtUML test bench, the motivations and rationale for model-based test will only be briefly described. The focus will be hands-on. And so this presentation is best done with a running copy of Bridgepoint in front of you. So plan on watching this through and then perhaps watching the recording at xtUML.org or found on YouTube, watching it again step by step with Bridgepoint in your hands. So we'll go through an introduction of the topic of test benching and model-based tests. And then I will record specific steps for your reference on how to build an xtUML test bench. And then using Bridgepoint, we will walk through building an actual test for our case study, the GPS watch model, and then wrap things up by reviewing the motivations for model-based test again at the end. The benefits of model-based testing include early testing, and I'll refer you to a presentation that was given a few weeks ago using the model verifier and describing how xtUML, being an executable modeling language, allows you to begin running your model, executing it, seeing if it's doing the right thing right from the very first day. And using the principles of test-first design, you can build in parallel with building your application component, you can build a test bench component that will allow you to test every feature as you add it. Productivity is improved for the same reasons that productivity is improved for your application. You can build tests faster and more accurately, working at a higher level of abstraction, the same way that you build applications faster and more productively and more accurately using a higher level of abstraction. So model-based test leverages all the same reasons for being model-based that an application does. Then you get the added benefit of consistency. If your tests are in the same language as your applications and at the same level of abstraction, then those skills can be transferred from a test group to a development group and vice versa. And then one of the big points and special advantages of executable translatable UML is that these test benches that are built can be reused at lower levels of abstraction. So we build the tests at the xtUML level, we execute our models beginning from the very first day, and at the end when we have application models together with test models, we then deliver these artifacts to the design teams and who will generate code and work at the target level of abstraction. Well, we can translate the test bench just as easily as we can translate the application components, and so we can run those test benches again at the next level of abstraction down on the target. We've seen this slide in previous presentations, and it simply highlights the increasing level of abstraction from when applications were developed at machine code, assembly, VHDL, RTL down here at the lower levels, and that the abstraction has risen and risen, and that UML simply represents another level of abstraction higher. Levels of abstraction beyond that also exist, and we'll continue to increase productivity by pushing the level of abstraction up. Next, we have a sequence of screenshots taken from Bridgepoint that we will use to explain the various parts of testing at the xtUML level. So the testing is going to start with the application. The application is packaged as an xtUML component, which is a black box that has functionality that is hidden from the outside world, except where it is exposed through an explicitly chosen interface. In this case, the interface has a name called I/O. For that application, we will bring a test bench. And the test bench is another component that has an interface with the same name, but has the opposite connection. So this is a compatible interface that can connect to the application component over the specified interface, and this test bench component will be used to create behavior to send messages back and forth across this interface to stimulate our application component and measure its response. This picture just shows all of both of the application component and the test bench component just in a library package side by side with the interface description for this interface that these share. Notice that the I/O interface has multiple messages. In this case, these are signals that are sent across the interface, and these signals can go in various directions. The connect message goes from it's to the provider, so it'll go to the component that has the ball end of the interface. The accepted message comes back the other way. Data goes from the requiring side of the interface to the provider, and the ACK gets sent back. And notice that the ACK has a parameter that gets sent. So these are the messages that we will use in our test bench to stimulate the application and measure its response. In this diagram, we have brought the application component together with the test bench component and wired them together into a test configuration. Let's consider a more complex application. In this application, we have three components, component A, B, and C, and notice that there are some internal interfaces between these application components. We see that A has an interface with B that it can communicate and send messages, as well as B communicating with C. And then there are these additional interfaces that communicate with the outside world. Well, we can build a test bench for this more complex application simply by building a bigger and more complex test bench. So we build a test bench, and the key is that we provide compatible interface references that can be connected to the application, whether the application is a single component or whether it's multiple components. Then we can bring the application and testbench together. Notice this highlights the compatibility of these interfaces one with another here on the testbench connection to the application. And in the same way as we did with a single component with a single testbench, we can bring them together and wire them, actually connect those interfaces into a test configuration where we can then run a test, and our test model will have application information inside here that is stimulating and gathering responses across each of these interfaces. One last point to make before we move into the specifics of how to is this idea of swapping various test configurations. I'm showing two test benches here. I've got A test bench and B test bench, and right now the B test bench is wired to the application. But it's just as easy to unwire that one and wire up the A test bench. What this allows me to do is to swap in various test configurations without much effort at all. I just need to create multiple configurations referencing these components. So I don't need to remodel or disconnect and reconnect anything. It's possible to have multiple test configurations using multiple test benches and allow for the separation of performance testing from functional testing, from boundary condition testing, and give you lots of options to drive your tests. And now for the step-by-step of building a test bench. Step one is to have the test benching project in your workspace together with the project you are testing. The test benching project can be found on github.com/xtUML models, and in fact in the upcoming demonstration we'll actually go check that out and bring that into the workspace. Step two is that you need to make sure that you enable interproject references in the project preferences of the project that you're testing. We'll be testing the GPS watch, and if you right-click on the project in the xtUML modeling perspective, it gives you a menu item to select project preferences, and you want to make sure that this checkbox is turned on. The third step will be to copy the sample test bench component from the test benching project and copy it into a package in your own model, and in our example we'll use GPS, and then rename that copied component, that sample test bench component, rename it to something that makes sense for your project. And in our case study we are going to build a test bench that replaces the user interface to drive the rest of the application. And so we copied sample test bench from the test benching project into the GPS watch project and then renamed it in a way that makes sense. Step four is that when you copy that sample test bench, it has the correct interface on the top that goes to the test sequencing component, but it has a bogusly named interface reference on the bottom, and it even has a name, something like rename this. And so you need to either rename or replace that lower interface with the one that is compatible to the interface that you'll be driving messages through as part of your testing. So far, we have leveraged the existing work of the provided test benching framework by copying the component in. Well, now the real work begins, and we need to modify the behavior of the test bench component so that we send and receive messages across the lower interface to and from the component under test. And inside the test benching, our new test bench is a class diagram that has a supertype test case with subtype test case classes. You'll have one of these subtype test cases for each of your tests. The first two are provided you simply modify them. After that, you need to begin copying them. Each class has a state machine that has these four phases, which we saw in the test benching sequence diagram, that every test goes through setting up, executing, cleaning up, and reporting results. So you'll be double-clicking on these states and adding additional behavior, perhaps even adding states to these state machines for each test case. And the adding action language is how you modify that behavior. So just to review, there are two test classes already in place. If you need to add a third test case, you will copy one of those subtype classes and paste it in underneath the supertype class, rename it, give it a unique name, unique number, and unique key letters. Then when you copy a class, the events need to be reassigned, and so once you've pasted that state machine in, go in, assign the events to be the same as in the first two state machines, and then begin modifying those states by editing the action language and adding states as you require. Okay, so now you will have a test bench component that has a test case in it that is capable of driving messages across a lower interface into the rest of the application. So now it's time to wire that test bench into a test configuration in a component diagram. So in this case, this is our test bench component, and we wire it in to our application. And then additionally, we wire in the test runner component, which is referenced from the test benching project. Then we have everything we need to fire up the model verifier and run it. As you're adding tests, there's one additional step that was not mentioned in step 5, and that is that for each test there's an initialization stanza in the setup method of the test case class. That's the supertype class. And by default, the subtype is created and related and initialized. And so for the first two test cases, you probably won't need to do anything, but for test cases 3, 4, 5, and however many that you have, you will need to create these stanzas in that setup operation in that test case class. And then those are the steps that it takes to build your test bench. Next, we will fire up Bridgepoint and actually go through these steps. Next, we open up a sequence diagram inside of Bridgepoint that illustrates the overall test benching test runner architecture. This sequence diagram shows the test runner component communicating to, in this case, sample test bench, but this will be any test bench that you have built into your testing model that follows this same protocol. And the best way to do that is to follow the instructions of copying this sample test bench into your project and then making modifications. And then your design or model under test here is what will be the actual components receiving messages and being driven by your test bench, which is from a high level perspective driven from the test runner. So every test scenario follows this same sequence of messages. At the beginning of a test, the test runner will send a discover message to the connected test bench, which gives that test bench an opportunity to respond with a message that registers the test, and it gives the version of the test suite and the number of variations, the number of test cases that it wants the test runner to sequence through. Then this next set of messages is repeated for each test case variation. So the test runner will send a setup message with your variation number, and your test bench can say that it's done with the setup phase. The test runner will then tell your test bench to execute the test case, the particular variation, and after that execution is complete, it will respond with done. In between that execute and done stage, your test bench will do some amount of stimulation on your design under test, getting various responses and determining whether those are correct. Backing up a little bit, at setup, when you get the setup message, you may be sending some messages to your design under test to set up initial conditions. So then after the setup phase and execute phase, the test runner will send a cleanup message, which will allow you to reset your device under test and do any cleanup that you need to remove cruft that you've created during the running of the test of the particular test variation. And then lastly, the test runner will ask you to report the success or failure of your run, and you'll send a Boolean variable that's true if your test case passed and which variation that ran. At the end of the number of test cases that you have registered in the registration message, the test runner will then give a summary report of how the whole system, of how the whole test bucket, if you will, how it fared, and with a summary of which test cases passed and which ones failed. Next begins the really practical portion of the presentation. I've started up Bridgepoint and will load up the models for a real test benching application. I will check them out from GitHub and go through each of the 7 steps that were listed previously and run the entire test. So the best way to take advantage of this is to follow along with me. So first, I will open the Git repository exploring perspective. And I will clone a Git repository and add the clone to this view. This now asks for some website information, and on github.com we have the models in the xtUML/models repository. So let me go to GitHub, to that location, github.com xtUML/models, and there's a little button here that I can push to get this information, and I want HTTP is an easy transport mechanism to work with. So I'll copy that to the clipboard and simply paste that in to my URI location there, and then type in my user ID and password, allow that to be stored. It's going to get the branch information. I only want the master branch. And now this is the location where the repository will be stored on my machine. And this is in my home directory, and that's fine. Do not store your repository in your workspace. So I'll finish and let that run. This is now downloading all of the models from xtUML/models onto my machine. Once I have that cloned on my machine, I will then import the project that I want into my workspace. Once I have the repository cloned, now I can import the project that I want into my workspace. For this work, I want to import test benching. Selected it for me, finish, let it refresh, and then if I switch to the xtUML modeling view, here I have my test benching model where I can begin working with it. Next, I will import the model that I want to do testing with. So I'm going to go back to my Git repository and import the GPS watch. First thing I need to do with my GPS watch is turn on the interproject references. I need the GPS watch application and the test benching application to be able to share interfaces and components. Next, I'll open up the GPS watch library module. This is where all of the application components are, and I will copy this sample test bench component into this library package of the GPS watch. Okay, now I'm going to close the test bench components so that I don't get it confused. And here I have the sample test bench. Let's open up this package and we'll see here right next to the UI component is this sample test bench component, and I want it to be compatible with this UI component, and so I need to make sure that it has an interface on the bottom that matches it. And now I will add in the compatible provided interface. And so now we have a lower interface on our test component that is compatible with the lower interface of the component that we're going to replace. And yet there's also an upper interface that will connect into our test bench. And actually this connection on the top goes to our test sequencing. Let's rename the component to be UI test bench. And now that we have this library package with all of our application components, let's take a look at the system configuration that we use for deployment. That one is called System. And here's where the UI connects into the tracking, location, and heart rate monitor. And so to drive a test of these lower three modules, I want to replace this UI module with my test bench, and then above that have that UI test bench being driven by my test sequencer. So I will create a new package and I will call it System TB UI. And in here, I will create a new component diagram that has all of the system components that we need. So I'm going to add the location component, and the tracking component, the heart rate monitor, and these I can connect up. So if I look at a bigger picture of this, I've got the bottom three components from my deployment. Now I'm going to place a test bench component here. So instead of the user interface, I will assign this to the user interface test bench. Wire that in since it's compatible. And now I need something to drive the test sequencing. So let's place our test sequencing component, a reference, test runner, up here at the top. Okay, we now have a full test bench wired together. Next we'll want to run this. It may seem a little premature to actually run, but this UI test bench module comes as a copy of a framework that actually has some intelligence built in to start with. So let's move to our xtUML debugging perspective. We'll create a debug configuration to run this model by double-clicking on the application. We'll give it a name, GPS UITB. We want to select the system test bench UI package, and we want to turn off simulated time and run in wall clock time and enable the logging of the activities when we run. So I'll start up the simulator, and the default framework is designed to fail by default, so we have to actually enhance the test case so that it will run successfully. But we see that it did run, and we get, looks like 2 test cases failure, and the overall bucket is done. So there's 2 test cases built into the test bench, and they failed. So let's go look in there. Let's make a real test case that sends real messages to our component under test and make something that actually works. Okay. Here's our new test bench component. If we look inside, there is a class diagram that has a supertype class called testCase with subtypes, and each subtype represents one particular test variation. There's a state machine that drives the overall test, and then each test case goes through a very simple sequence. Every test case always has to go through setting up, executing, cleaning up, and reporting results. Right now, the actions inside these are just sending the response back to the test driver that says that it's finished this phase. Each time, assuming that it's successfully finished the phase, but then when reporting the results, notice here that we send back whether the test case has passed, and that value has been set to false, such that when we send it back, we're going to say that the test case failed. And so we need to set that to true at the point in the test case where we are happy with our results. So let's modify this state machine to make a real test case for the GPS watch user interface and see if we can get a successful run that actually exercises the GPS watch. Okay, now let's make a real test case. Let's set some context. Looking at the overall deployment package, we have a user interface where buttons are going to be pressed and messages are going to be sent to the tracking component, which will then communicate with location and heart rate monitor. We now have substituted in a test bench for the UI component with a test driver that will sequence a series of test cases, sending messages across this interface and checking for the expected response. So now we need to build a real test case. There is a sequence diagram that actually gives us the ordering of the messages for the scenario that we want to test. And this is the start, stop, reset sequence. And this sequence diagram shows the user actor interacting with the user interface, tracking, location, and heart rate monitor components. And as you'll notice that the user only interacts with the user interface, and that the user interface only interacts with tracking. And so our user interface test bench is going to deal with these messages that are communicating between these two components. The scenario that we want to test is illustrated here, where the user, with his fingers pushes a button on the user interface, which causes the start, stop, pressed message to be sent to tracking, which triggers a lot of interaction between the tracking, location, and heart rate monitor components, but we're interested only in this communication between tracking and the user interface. So once the start, stop, pressed message is sent, the tracking component will begin sending time and data values back to the user interface to be displayed up until the point that start, stop, pressed is pressed again by the user pushing the button, which then sends the message between the components. And then to totally end the sequence, the reset button is pressed, which will reset the display back to its initial values. So what our job is to do is to build a test case that sends these messages, start, stop, pressed, start, stop, pressed again to cause it to stop, and then to send the reset, and in the meantime at least get notification from one of these other messages. So what we need to do is to modify the internal behavior of our test bench component to provide that capability. We'll modify the class diagram, and then we'll spend more time modifying the state machine that causes those messages to be sent. Modify the standard framework here was that I added an attribute, running, which is of type Boolean, to the simple test case class, and this attribute is used to be set true when a message is received back from the tracking component back across this interface to the user interface test bench component. In our sequence, it's this message here. So as soon as this message is received, then I'll set that value to true. That occurs right in the port message. Set time here, so that when this message is received, I'll select the test bench simple test case, and I'll set this running attribute equal to true in that spot. The rest of the modifications occur in the state machine. So in the setting up state, we initialize the test, this running attribute that we added on the class diagram, to be false. So meaning we have not seen communication from the client. Then we modify the executing state to actually send the start stop pressed message, and then start a timer that will delay for 2 seconds to allow for a response. After that 2 seconds, this event will fire, taking us into the checking response state, which will, if we see that we did get a response, then we'll select the parent test case and we'll mark it as having passed. This will be true. Then we will send start stop pressed again to cause the tracking component to stop ticking, and we'll send our message back to the test runner that says that we have finished the executing state of our test. The cleaning up state, to do cleanup, we simply send the reset message down to the tracking component, and then the reporting results is not changed. It's unmodified. We will be sending the test case passed attribute, and if we did see that message coming back from the tracking component, this will be passed and our test case should succeed. Switching now to the xtUML debugging, we will start up the verifier, execute our test case. We're expecting test case 1 now to pass if everything's good. Test case 2 we expect to still fail. We haven't touched it. So we get the summary here. Test case number 1 passes. Test case number 2 fails. Bucket done. We have a legitimate test case. Once we clear that, we move back to xtUML modeling, and we can look at what it takes to add a second test case. The second test case is, we get a lot of help because the framework comes with another second test case class, and it's got a state machine identical to the first test case, which we can then modify to use a different scenario to run a different test variation, and it will be automatically included in the bucket of tests. When it comes time to add the third or the fourth or the fifth test case, then we copy one of these classes and paste it into place, And then we can connect it into the subtype hierarchy. And then we can edit its state machine. And we need to reconnect the events because those don't come across when we copy. So we can assign them the correct events, connect them up, and edit the state machine in the same way as we did for test cases 1, 2, and 3, only now we'll be doing yet another test scenario. Talked about reuse and reusing these test models down at the next level of abstraction. So let's see what that looks like. And I will build this project and generate the code and compile it for the PC platform. And so I launch the model compiler, allow the files to be translated into C. The next step will be the compilation, where it takes all of the C files and compiles them. And I see that I've got my generated C code. The model compiler trace is here. And now I can run this and hopefully see the same tracing information that we saw when we were running with the model verifier. So I'll let it run. We get some trace, and hopefully we get test case 1 passed, test case 2 failed. So we have now run the models and reused the test bench, even the application and the test bench, down at the next level of abstraction at the C, C++ level on the PC target in this case. Now you have heard the steps for building a test bench in xtUML, and you've actually gone through, hopefully together with me, on building a test bench, connecting it up and executing it using Bridgepoint. And so just a brief review then of why we do this. Model-based testing in xtUML allows for early testing. We can run our models from the very first day, literally, and using test-first principles, we can build our test bench component, perhaps even before we build our application component, run it, see it fail, then build an application component that will satisfy the requirements placed on it by the test bench component. Our productivity is much better in xtUML for building tests for the same reasons that our productivity is better for building our applications. We're at a higher level of abstraction, we're executable from the beginning, and we can get work done faster. And by having our test bench and our applications in the same language, it gives us a consistency and flexibility with using engineering skill across both test and application development disciplines. And then at the very end, we just saw that you can, once you have built these test benches, they translate with the model compiler just like the applications do. And so the test benches can move out into the lab and off of the modeling tool desktop and get reuse downstream, which is a very big benefit. Thank you for spending time with me and learning about xtUML test benching and model-based test. Be sure to visit xtuml.org, download these materials off of GitHub, and build test benches for your own application. Thank you again. Bye for now.